Hello everyone and welcome to today's video lecture on the beta function. The beta function is a very interesting and important function in its own right, and it's closely related to the gamma function. And we're actually going to use one of the important properties of the beta function to prove something called the Legendre duplication formula for the gamma function in the video following this one. So all I'm going to do today is motivate and define the beta function. This is a function which has two inputs, and we're going to prove probably the most important identity for the beta function, which is that beta of z1 comma z2, again those are the two inputs for the beta function, equals gamma of z1 times gamma of z2 all over gamma of z1 plus z2. So our work in this video to develop the beta function really builds on the work we did in our video on the integral form of the gamma function. So you may want to go back and watch that video. It's actually the most popular one on my channel right now. And in our development of the integral form of the gamma function, we studied the following integral. This was the integral from 1 to 0, okay, from 1 to 0, of 1 minus x all raised to the power of, let's say, n, times x to the c dx. So I'm going to rewrite this integral, but reverse the order in which the terms in the integrand are multiplied. So this will be the integral from 1 to 0 of x to the c times 1 minus x to the n dx. And we found in that earlier video on the integral form of the gamma function that this equals n factorial over c plus 1 times c plus 2 times c plus 3 dot 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 all the way up to c plus n times c plus n plus 1. Again, you can watch my earlier video to see how we derived that. Now, let's say for the sake of argument that both c and n are positive integers. If that's the case, then I can start playing around with this a bit. For example, if we change our variable n to n minus 1, we have the following expression. The integral from 1 to 0 of x to the c times 1 minus x to the n minus 1 dx would then equal n minus 1 factorial all over c plus 1 times c plus 2 times c plus 3 dot 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 all the way up to c plus n minus 1 times c plus n. That would be the last term in the denominator there, changing n to n minus 1. Okay, so I'm going to bring that to the top of the screen. Now we know from our work on the gamma function that gamma of n equals n minus 1 factorial. So we're already seeing a connection to the gamma function here, because we can write this expression as the integral from 1 to 0 of x to the c times 1 minus x to the n minus 1 dx equals gamma of n all over c plus 1 times c plus 2 times c plus 3 dot 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 times c plus n minus 1 times c plus n. So already the gamma function is starting to show up in this expression. And I just want to emphasize again that this line of reasoning is valid for n and c, both positive integers. That's how I was able to replace n minus 1 factorial with gamma of n. So looking at this expression now a little bit more closely, we might also be tempted to make a manipulation with the constant c in this expression. So let's do that. What if we changed c to c minus 1? What impact would that have on this expression? Then we would have the following. The integral from 1 to 0 of x to the c minus 1 times 1 minus x, close parentheses, to the n minus 1 dx equals gamma of n all over, and in the denominator we would have c minus 1 plus 1 times c minus 1 plus 2 times c minus 1 plus 3, dot, 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 up to c minus 1 plus n minus 1, and finally times c minus 1 plus n, close parenthesis. So we can simplify this a little bit, right? What we've really done is just reduced every term in the denominator by 1, so I'm going to make that simplification there. The denominator would become c times c plus 1 times c plus 2, dot, 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 up to c plus n minus 2 times c plus n minus 1. Okay, so let me just replace that in the denominator. So let's move that expression to the top of the page. And now I'm going to rewrite the denominator by reversing the order of multiplication. So then our integral will equal gamma of n over c plus n minus 1 times c plus n minus 2, dot, 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 all the way down to c plus 2 times c plus 1 times c. Again, reversing the order of multiplication for the terms in the denominator. But once I do that, when I look at the denominator, it feels like there's a missing piece of a factorial here. So what I'm going to do is multiply this thing by c minus 1 over c minus 1 times c minus 2 over c minus 2, and so on. So c minus 3 over c minus 3, and so on, all the way down to 3 over 3 times 2 over 2 times 1 over 1. By doing that, I've completed the factorial in the denominator. And in fact, in the numerator, I also have an expression equal to a factorial. I have in the numerator c minus 1 factorial. And here in the denominator, if I look at all of these terms being multiplied together, these would equal c plus n minus 1 factorial. So that's a pretty neat way of writing this expression, and I'm going to do that here. So this expression would equal gamma of n times c minus 1 factorial all over c plus n minus 1 factorial. And now I can put everything in this expression in terms of the gamma function, because c minus 1 factorial, that just equals gamma of c. So this thing becomes gamma of n times gamma of c. And then c plus n minus 1 factorial, that would just equal gamma of c plus n. So the integral expression equals gamma of n times gamma of c over gamma of c plus n. And this has been shown to be true at least for the narrow case where n and c are positive integers. So I'm going to move that equation to the top of the screen here, and let's put a box around it because it really is the take-home message from today's lecture. But so far we've only shown that this relationship is valid for n and c both positive integers, when in reality the gamma function extends the factorial to include other inputs such as positive fractions and negative fractions. So what we do still need to do is show that this relationship is true for all the possible valid inputs for the gamma function. In other words, for n and c, wherever the gamma function is defined. So our goal here is to prove in full generality that gamma of u times gamma of v all over gamma of u plus v, that this equals the integral from 1 to 0 of x to the u minus 1 times, open parenthesis, 1 minus x close parenthesis to the v minus 1 dx. Okay, we're going to prove that for any valid input for the gamma function. So we're going to rely on the integral form of the gamma function for this proof. So we have that gamma of u times gamma of v, using the integral form of the gamma function, would equal the integral from infinity to 0 of, let's use the dummy variable s, to the u minus 1 times e to the negative s ds, times the integral from infinity to 0, we'll use a different dummy variable here, we'll use t, t to the v minus 1 times e to the negative t dt. And now I can combine those two single integrals into a double integral as follows. So the double integral from infinity to 0 of s to the u minus 1 times t to the v minus 1 times e to the negative s times e to the negative t ds dt. All right, so we have our double integral there. And now I'm going to combine terms in that part of the integral. So this will just be e to the negative s plus t. All right, so I'm going to write that in there. Let me just erase that part and rewrite the integral in that way. So this again will be times e to the negative, open parentheses, s plus t, close parentheses. That's our double integral there. And now we're going to make an important variable substitution. Okay, we're going to let s equal x times y, and you'll see why we're doing this in a moment. And we're going to let t equal x times, open parentheses, 1 minus y, close parentheses. Or, in other words, t will equal x minus x times y. Now, it may be opaque as to why we're making these substitutions, but it will become clear in a moment. So based on those substitutions, then, s plus t would have to be x times y plus x minus x times y. And then the xy terms just cancel, and I'm left with s plus t equals x. Okay, so I'm going to take all of that information that we've established and put that to the side of the screen for reference as we move on to calculate this integral. So the next thing we need to calculate is what ds dt would equal with this variable substitution in x and y. So ds dt will equal the absolute value of the determinant of the Jacobian matrix times dx dy. This might be the most advanced step in this video, especially for people that aren't familiar with multivariable calculus. So again, J is the Jacobian matrix for our transformation, and we'll set it up this way. So we'll say J equals, it'll be a 2 by 2 matrix here, so let me draw my brackets. And then in row 1, column 1, we'll have del S, del X, that's a partial derivative of S with respect to X, and then del S, del Y in row 1, column 2. Row 2, column 1, del T, del X, and row 2, column 2, del T, del Y. Okay, so those are our partial derivatives. And now let's compute these partial derivatives. So del S, del X, that would be treating Y as a constant here. So we differentiate S with respect to X, treating Y as a constant, and we just get Y for that partial derivative. Del S, del Y will just equal X because we're treating X as a constant for that partial derivative. And then del T, del X would equal 1 minus Y. And then to compute del T, del Y, well, let's just flesh this out a little bit. T equals X minus X times Y. So treating X as a constant here, del T, del Y, that'll just equal 0 minus X, or just negative X. Okay, so that's our Jacobian matrix. Now let's take the determinant. And to do that, the determinant of J is going to just equal del S, del X times del T, del Y minus del S, del Y times del T, del X. All right, and we know what these partial derivatives are. We just computed them, so that will equal Y times negative X minus X times 1 minus Y and that will just be minus X times Y minus X, and then a double negative, so plus X times Y. The xy terms cancel, of course, and we're left with negative X as our determinant of the Jacobian matrix. So determinant of J equals negative X. And then when we take the absolute value of that, This just equals x whenever x is a positive number, which we'll see momentarily is the case here. So finally, ds dt will equal the absolute value of the determinant of the Jacobian matrix, which we just computed to be x, when x is positive, times dx times dy. So ds dt will just equal x times dx times dy. Okay, so we're making progress on computing this double integral. I'm going to write that fact over here. ds dt in this variable substitution will equal x times dx times dy. So that's an important piece of information, and I'm going to just put a box around that there. And now we need to consider our bounds of integration and whether our variable substitution has changed them. So let's consider. We know that x equals s plus t, and in the integral as I have it written here, with s and t as our dummy variables, we know that s is anything greater than or equal to 0, and t is anything greater than or equal to 0. Those both range from 0 to positive infinity. And x is the sum of s and t, which means that x must be greater than or equal to 0 also, or rather, we can say x ranges from 0 to positive infinity, as a limit, of course. Okay, so our bounds here in x are that x ranges from 0 to a limit of positive infinity. Okay, great. So that's fine for x. Now what about y? Now we know that y equals s over x. Okay, looking at the right, what we have in the box there, s equals x times y, so y must equal s over x. But we know that x equals s plus t. So we conclude that y equals s over s plus t. And again, we have that s can be anything from 0 to positive infinity, and t can be anything from 0 to positive infinity, right? So for any fixed s, as we let t range to positive infinity, this expression for y will go to 0. Similarly, for any fixed t, if we let s range to positive infinity, the ratio s over s plus t will equal 1 in the limit. So there, y would equal 1. So the bounds for y are therefore from 0 to 1. And that's the last key piece of information we need to compute this double integral with our variable substitution, that y ranges between 0 and 1. So I'll put that there on the side. And now we have gamma of u times gamma of v equals the double integral of x times y, subbing that in for s, to the u minus 1, times, subbing in for t, x times 1 minus y, close parentheses, to the v minus 1, times e to the negative, well, we know s plus t equals x, so e to the negative x, times x dx dy, which we found to be equal to ds dt. And now let's write in our bounds of integration. So for the inner integral, which is in terms of dx, that's infinity to 0. And then for the outer integral in terms of dy, that's 1 to 0. So we have the double integral from 1 to 0, infinity to 0, of x to the u minus 1 times y to the u minus 1, I'm just distributing the exponent there, times x to the v minus 1, times, open parenthesis, 1 minus y, close parenthesis, to the v minus 1, times e to the negative x, times x, which I'll write as x to the first power, times dx times dy. Okay? And now I'm going to combine all of my terms in x. So I get the integral from 1 to 0, infinity to 0 of x to the u minus 1 plus v minus 1 plus 1 times e to the negative x times y to the u minus 1 times 1 minus y to the v minus 1 dx dy. So I'm going to move that integral to the top of the screen there, and now we're going to actually compute it. So starting with the inner integral, which is in dx, all of those y terms would be treated as a constant, so I can pull them out of that inner integral. So it'll be the integral from 1 to 0 of y to the u minus 1 times 1 minus y to the v minus 1 times the integral from infinity to 0 of x to the u plus v minus 1 times e to the negative x dx dy. Now if we look at that inner integral, which is only in x now, we see that we actually have an expression equivalent to the gamma function with our input as u plus v. So that inner integral actually equals gamma of u plus v. That's pretty cool. So we have the integral from 1 to 0 of y to the u minus 1 times 1 minus y to the v minus 1 times gamma of u plus v dy. Now within this integral, gamma of u plus v is just a constant, so we're going to get gamma of u times gamma of v equals gamma of u plus v times the integral from 1 to 0 of y to the u minus 1 times open parenthesis 1 minus y close parenthesis to the v minus 1 dy. So I'm going to bring that equation to the top of the screen there, and now we're very close to being done. If we divide both sides of our equation by gamma of u plus v, we get that our integral expression, the integral from 1 to 0 of y to the u minus 1 times open parenthesis 1 minus y close parenthesis to the v minus 1 dy, that will equal this beautiful formula, gamma of u times gamma of v over gamma of u plus v, close parenthesis. Now, there we have it. Now, this integral expression that we've written here actually gets a special name. It's called the beta function, where we take as our inputs u and v. Beta of uv equals gamma of u times gamma of v over gamma of u plus v. And now we've proved this equation in full generality, not just for positive integers. So thanks for watching. I hope you enjoyed this video, and if you did, please like or subscribe to my YouTube channel. Thanks again.